You know, we usually expect planets to follow a pretty standard set of rules. You orbit a star, you spin on an axis, you get a day and a night. Pretty simple, right? Well, not Venus. Venus completely ignores the standard rules of orbital mechanics. It's this bizarre place where time literally just doesn't work the way we're used to. In fact, Venus is the only planet we know of where a single day actually lasts longer than its entire year. Let that sink in for a second. It takes 224 Earth days for Venus to complete one lap around the Sun, but it takes 243 Earth days just to finish one full rotation on its axis. So yeah, it literally finishes its year before it even finishes its day.
A day longer than a year. When you compare Venus to the rest of the neighborhood, looking at everyone from Mercury out to Jupiter, it is a total outlier. Not only is it spinning incredibly slowly, but it's spinning backwards. It's in a completely retrograde rotation. So while almost everyone else in the solar system is turning counterclockwise, Venus is just out there slowly spinning clockwise. Because it spins backward while moving forward around the Sun, the actual experience on the ground gets completely warped. Factoring in that retrograde rotation, a visual solar day on the surface, meaning the time from one sunrise to the next, is about 117 Earth days. And thanks to that backward spin, the Sun actually rises in the west and sets in the east.
Tracking the giant disco ball. Now, we actually thought we had this rotation rate nailed down back in the early 90s using radar data from the Magellan probe. But then, the Venus Express orbiter arrived in 2006 and found something weird. Massive surface features were up to 20 kilometers completely out of place from where Magellan said they should be. The length of a Venusian day wasn't just slow, it was actively shifting.
Figuring out exactly what was happening took a 15-year campaign by researchers at UCLA, and their method was wild. They essentially used giant satellite dishes here on Earth to bounce a massive radio signal off Venus. They were tracking the reflection across our planet, kind of like a giant disco ball, catching the signal on one coast and then a few seconds later catching it on the other coast, just to measure the planet's exact speed.
And what that 15-year tracking campaign revealed is honestly pretty crazy. The planet's rotation actually fluctuates by up to 20 minutes. So why does it do that? Well, Venus has an atmosphere that is 50 times denser than Earth's. That super heavy, fast-moving air literally drags against massive mountain ranges, constantly trading momentum with the solid crust. It's so thick that the weather is physically altering the spin of the entire planet.
Why Venus spins backwards?
For a long time, planetary scientists were basically split into two camps on how this happened. Early theories leaned heavily on the giant impact hypothesis, the idea that a massive collision early on just physically knocked Venus upside down. But current physics points toward the tidal evolution model, which is a much smoother, inevitable process driven by the planet's own environment.
It's essentially an epic tug-of-war that played out over billions of years. First, the Sun's immense gravity pulled on the solid body of Venus, creating friction that slowed its forward rotation. At the exact same time, the Sun was intensely heating that thick atmosphere, creating a massive pocket of hot air, or a thermal bulge. Gravity then pulled on that specific thermal bulge, essentially grabbing the steering wheel and pushing the planet into a slow, reverse spin.
And we can actually prove this through advanced mathematical models like the creep tide theory. The math shows that if Venus didn't have its heavy atmosphere, the Sun's gravity would have locked it into a normal forward-facing spin a very long time ago. It's entirely the sheer weight and the thermodynamics of the atmosphere that overpowered the original momentum and forced the planet backwards.
The super-rotating atmosphere.
So while the solid rock of the planet takes those agonizingly long 243 days to turn, the upper atmosphere zips around the entire globe in just 4 days. It's a phenomenon called superrotation. On Venus, the planet spins so slowly that the atmosphere exists in this rare state of cyclotrophic balance. Basically, hurricane-force winds are moving so fast that they perfectly balance out the atmospheric pressure.
Data from orbital probes, like Japan's Akatsuchi, proves this superrotation is essentially a giant self-feeding engine. The Sun just cooks the day side for months on end, creating a massive temperature difference between the day and night sides. That intense contrast excites huge thermal tides that push the atmosphere around the globe. Add in heat migrating toward the poles and gravity waves breaking in the upper clouds, and you get this perpetual high-speed atmospheric churn.
The exoplanet connection.
Understanding this isn't just about Venus, though. It actually changes how we look at the rest of the universe. See, we used to assume that planets orbiting close to small red dwarf stars would suffer from something called tidal locking.
That's when a star's gravity forces a planet to perpetually show the exact same face to the star. So one side permanently boils, the dark side permanently freezes, the atmosphere collapses into ice, and the whole planet just becomes a dead zone. But Venus completely changes the game here. It shows us that a thick atmosphere can generate enough of its own torque to overpower that gravitational lock. A strong atmosphere can keep a planet turning just enough to distribute heat globally. And this is huge, because it means rocky planets orbiting close to red dwarfs might not be frozen wastelands after all. Their atmospheres could actually preserve a stable climate, maybe even liquid water.
The next Venus missions.
Because there's still so much we don't know, a brand new fleet of spacecraft from NASA and the European Space Agency are finally heading back in the early 2030s. We've got Veritas and Envision, which will map the surface and the planet's gravity field with unprecedented radar. And then there's Da Vinci, which is literally going to drop a chemical sampling probe right through those dense, crushing clouds to taste the atmosphere on the way down.
With all these next-generation tools pointing at our weirdest neighbor, we're about to get answers to some massive questions. Remember, Venus and Earth started with the exact same ingredients, yet one became a paradise and the other became a slow-spinning, backward pressure cooker. What kind of active churning geology are those probes going to find hiding in the dark? And more importantly, what exact turning point sent Venus down such a radically different path?
What the fact? Follow for more.